Hello. Here's part 2 of your table and trig limits video. I'm sorry that it's in 2 parts. There were some technical difficulties. So we are now going to look at trigonometric limits. And one of the ones we're going to look at is the limit as x approaches 0 of sine x over x. And this is evaluated by looking at the graph and looking at the table on your calculator. And I really shouldn't have flipped my laptop closed because I'm going to do this in Desmos because Desmos is my favorite thing. So if I come over here and go to Desmos, and then go to the graphing calculator, I am going to graph y equals sine of x divided by x. Cool. Now we wanted to look at this where x approaches 0. And if I look as x approaches 0, this seems to really be going toward 1, don't you think? So let me set my labels here at step 1. Yeah, that definitely looks like it's going toward 1, right? I would agree. So it seems that that's going toward 1. Let's look at the table for it. Oops, let me divide that by x and then make it a table instead. Yeah, that definitely seems to be heading toward 1 because if I change this to 0.001 and that to 0.001, yeah, those are definitely heading toward 1. But at 0, it's undefined. Okay, so evaluate the limit by looking at the graph and looking at the table. Cool. This goes to 1. Yeah, but why? I mean, obviously the graph does, but that's not really good enough for me. Just, oh, the graph seems to go there. I guess I can live with it. I don't want to live with it. I want to know why. So let's try to evaluate the top and the bottom. So if I look at the limit as x approaches 0 on top, I get 0 because the sign of 0 is 0. And on the bottom, it's also going to 0. So I have 0 over 0, which in the past has meant we could like factor and cancel, but this time I can't factor and cancel. Gosh, I wonder why that's going toward 1. So if we go back here and I look at Desmos again and I ditch these and I say, okay, what if I just look at y equals sine x and I look at y equals x and I think about them independently? Well, here's y equals x, here's y equals sine x. If I take the quotient of two things and I get 1, that means that the two things were equal, right? 7 divided by 7, negative 2 divided by negative 2, you get 1. So that means that near 0, the graph of y equals x and the graph of y equals sine x look alike. Did I say near 1? I meant near 0 if I said near 1. Near x equals 0, y equals sine x, and y equals x look alike, which, I mean, appears to be true. Outside of 0, they definitely don't look alike. But near x equals 0, they look alike. And if I want, I can zoom in here, hypothetically. Come on. Oh, I'm touching the wrong part. Yeah, near 0, they do look alike, don't they? And fun fact, you can ask Mr. Sweeney this, but he and I were having a conversation one day and we were talking about limits and he went, oh my God, that's why we use the value instead of sign. I said, what are you talking about? And he said in physics, when they are doing physics on radians or for small angle values, they use the value of the angle as the sine value. They don't actually calculate sine. And it's because y equals sine x and y equals x are so similar. So if you wanted to know the sine of 0.2 radians, it's about 0.2. If you want to know the sine of 0.16 radians, it's about 0.16. It's kind of a cool thing. So apparently scientists do this. I didn't know that. I thought it was pretty cool. So long story short, sine x over x as you approach 0, not other things, goes to 1 because near 0, sine of x and y equals x look a lot alike. Then it says, look at y equals, that should say 1 minus cosine x over x. So the limit as x approaches 0 of 1 minus cosine x over x. Let me zoom back out for a moment here. So y equals 1 minus cosine x divided by x. Okay, well, that's what that thing looks like. And that's headed towards 0. Okay, and if I look at the table here for that one, 1 minus cosine x divided by x, and I make that thing a table, let's see, if I change this to 0.001, yeah, that's a tiny number, and I change this to 0.001, yeah, tiny number. So that thing's going to 0. I mean, I can live with it. And let's think about why that would be. Well, if I look at the limit as x approaches 0 for the top, I have 1 minus cosine 0, and the bottom goes to 0, but cosine of 0 is 1. So this is one of those things where the fraction goes to, hey, here, come on in. Hang on, guys, let me just pause this. I can edit it, it's fine. Hang on. No, I'm making a video. Okay, so we have this y equals cosine x, and it heads towards 0. And I don't know where I was because somebody popped in my room, but that's okay. So let me go back to our notes here. And we have decided that sine x over x goes to 1. And as x approaches 0. And 1 minus cosine x over x goes to 0 as x approaches 0. And now let's evaluate the other things. Before I get to that, let me show you one more thing. So let me ditch this. And I have y equals sine of 3x divided by 3x. Where does that thing head? Well, that also heads towards 1. So x over x headed toward 1, 3x over 3x headed toward 1. I wonder where maybe 6x over 3x heads. 2. What if I did like 15x? 5. Do you notice something that's happening? What if that was 15x over 15x? 1. Hopefully what you're noticing is when you look at sine of ax over bx, you just take the ratio of the coefficients. So when I do sine 3x over 3x, that's going to go to 1 because I have 3 and 3. Sine 5x over 3x is going to go to 5/3. All right, and I'm pretty sure this is supposed to say tan 3x. Sometimes when I print to OneNote, things disappear. Well, if sine 3x over 3x goes to 1, now all of a sudden we got tangent. Let me check. Do you like how I act here like I don't know what's going on? But obviously I really do know what's going on. So tan 3x divided by 3x. That's a crazy looking graph, but all I care about is near 0. That seems to go to 1. Well, let's try to change this. What if this was tan 6x over 3? That one goes to 2. What if I did like tan of 0.5x over 3x? Okay, where does that go? That kind of looks like it goes toward, I don't know, maybe 1/6. Tangent does the same thing that sine does. So if you have tan ax over bx, it's just the ratio of the coefficients. So tan 3x over 3x also goes to 1. All right, sine 5x over tan 2x. Let's see. Y equals sine of 5x divided by the tangent of, what was that? 2x. Oops. Where does that go? Seems to go to 2.5. 2.5 is 5 over 2. Look at that. I still get to take the ratio. So this is 5/2 or 2.5. So we have some general ideas now. So sine ax over bx goes to a over b. Tan of ax over bx goes to a over b. Sine of ax over sine of bx also goes to a over b. We just saw that sine of ax over tan bx goes to a over b. Okay, these all seem to work out with this a over b thing. What if I have sine squared of x over 2x? What? Here's where we're going to get a little bit creative. And we're going to say, you know what? Sine squared x is the same as sine of x times sine of x. And 2x, I can separate into 2 and x. So now what I can do is take the limit as x approaches 0 of sine x over 2 times sine x over x. So as x approaches 0, sine x over 2 goes to 0 over 2. And sine x over x, as x approaches 0, goes to 1. 0 times 1 is 0. And then if I have sine of x over x squared, I'm going to do very much the same thing. As x approaches 0, I'm going to have sine x over x times 1 over x. And as x approaches 0, sine x over x approaches 1. And as x approaches 0 here, I have times 1 over 0. That's going to be undefined. This limit doesn't exist. Okay? So that is how all of these work. So you want to get everything back into a form where you have sine AX over BX or tan AX over BX and kind of manipulate things to make sure that that works out. All right, that's the thing. We are done. So if I have a really bad joke for today that has to do with trigonometry, why does Mrs. Vibber always wear sunscreen at the beach? So I don't get any tan lines. Sorry, not sorry. Have a great day.